complex that for centuries, really the best we could do is get rough estimates.
Right.
We're talking about problems often labeled, unsolvable by exact methods.
Hmm.
Today, we are diving into a mathematical breakthrough that it fundamentally changes that whole picture.
Yeah, it's really fascinating. This new approach, Ezouidi's theorem, it actually provides exact symbolic solutions. We're talking precise answers, even for equations that everyone thought were just intractable,
Practical, right?
So our mission today in this deep dive is to show you how it works. We'll use a specific, pretty gnarly 16th degree polynomial as our main
A
example.
16th degree.
Yeah, and we really want to highlight why this theorem basically redefines what we even mean by solvable in mathematics.
So what does this actually mean for you listening? You might think, oh, math, it just has all the answers, right? But when you get to these high degree polynomials equations, where the highest power of x might be 16, or even higher, things get really interesting.
They do. Historically, if you needed to find the roots, those values of x that make the whole equation zero,
Yeah.
classical methods like Newton's method, they mainly just gave you numerical approximations, estimates.
Getting close.
Exactly. And the inherent problem with those approximations is, well, they're prone to error, especially as the complexity of the polynomial goes up.
Right, the errors get bigger.
They can, yeah. There's always this risk of rounding errors, which means they just can't guarantee exact values. It's kind of like trying to navigate a really dense fog with a blurry map.
Yeah.
You get close, maybe, but you never know if you're precisely at your destination. And for centuries, a huge theoretical roadblock was Abel's theorem.
Ah, yes, Abel's theorem.
Which fundamentally said that for polynomials above a certain complexity, you just couldn't find their exact roots using standard tools like basic arithmetic and square roots, cube roots, what mathematicians call radicals.
So you were just stuck with approximations?
Pretty much, that was the prevailing wisdom.
Okay.
So this raises a big question, right? If the classical methods fall short, how do we get exactness?
Yeah.
Ezouidi's theorem shows this precise path to the actual solvable roots. It uses a structured process that completely bypasses those traditional limitations. It doesn't just tweak the old methods, it sort of redefines the whole game for high-degree polynomials.
So the core difference then, the real game changer, is that Ezouidi's theorem lets you derive exact symbolic solutions, like the actual mathematical expressions for the answers.
Precisely, which is totally different from just focusing on approximations like the old methods did.
And what's really amazing is how it just cuts through the implications of Abel's theorem. It shows that even polynomials that do have these radical roots, they can be solved exactly.
Absolutely. It reveals there was this whole other route, a different way of thinking about it that we hadn't really seen before.
How does it do that?
Well, the theorem approaches the solution differently. It sort of breaks down the polynomial first and then solves for the roots symbolically. It uses this recursive process.
Recursive, meaning step by step, building on itself.
Exactly. It systematically finds these exact values, and crucially, it steers clear of any of those errors that pop up when you approximate. It's all about meticulously building precision, step by step, right from the start.
Okay, here's where it gets really interesting then. Let's look at the actual polynomial we're solving today. So imagine an equation. It's so long it would probably stretch right across your screen. It's got 17 different terms.
Yeah.
Climbing all the way up to x to the power of 16.
That's a beast.
It really is a formidable 16th degree equation. Just looking at it, you can see the complexity baked in.
Indeed. And the first step with Ezouidi's theorem isn't just, plugging in numbers or trying to guess.
Right.
Instead, we express this polynomial using a set of symbolic coefficients. Think of them like placeholders, scale. And these are then calculated recursively based on the original polynomial's terms.
Recursively again, so step by step.
Yes. Now, the specifics of the recursive formula itself are quite involved, maybe not essential to memorize right now.
Okay.
But conceptually, think of it like a highly structured iterative process. It systematically transforms the polynomial by finding hidden relationships between its coefficients, step by careful step.
So, if I'm trying to grasp that, this recursive thing is like a kind of mathematical daisy chain. Each step builds on the last one.
That's a good way to put it.
It takes bits of info from the original coefficients and combines them meticulously, maybe adjusting terms, with things called binomial coefficients. And it keeps looking back at earlier calculations as it goes along. It's a method that sort of gradually distills the equation down.
Precisely, it distills it. And now here's the truly surprising simplification that comes out of this systematic calculation.
Okay, I'm ready.
After you do all these recursive calculations for these symbolic roots, something really astonishing happens. Many of those coefficients, these terms we calculated, they just turn out to be zero.
Zero. How many?
Well, for this specific 16th degree polynomial, out of the 17 potential coefficients derived through this process, 15 of them just vanish. They become zero.
15 out of 17. That's incredible.
It is. We're left with only two non-zero coefficients, S7R and S15R.
Wow. So what starts as this huge sprawling 16th degree monster, thanks to Ezouidi's theorem, it just dramatically simplifies. It collapses down.
It collapses right down.
Yeah.
From that original complex form with 17 terms, it becomes just three elegant terms. Px by 16 plus S7R by 8 plus S15R equals 0.
By 16 and by 8 term and a constant. That's it.
That's it. The reduction in complexity is, well, it's truly astounding.
Yeah, no kidding.
And this kind of dramatic simplification, it isn't just a fluke for this one polynomial. It seems to be a really profound feature of how Ezouidi's theorem works.
So it finds a hidden simplicity.
Exactly. It's about the theorem's power to uncover these elegant underlying structures where, you know, classical methods just saw overwhelming, intractable complexity.
Right.
This isn't just about solving one tough equation. It's more like having a new lens, a new way to view, and maybe conquer a whole class of problems we thought were out of reach.
Okay, so you have this much simpler equation. By 16 plus S7R by 8 plus S15R equals 0. What happens next?
Well, from this dramatically simpler equation, we can then derive the exact roots using further symbolic calculations. It actually becomes something quite manageable. It leads us directly to a formula for by 8 first.
Ah, okay, so you solve 4 by 8.
Yes, and that allows us to find the final exact symbolic roots for x.
And what's really cool, you're saying, is that these roots aren't just close numbers from a calculator.
No, not at all.
They are precise mathematical expressions. You mentioned complex exponentials.
That's often how they turn out, yes. Complex exponentials are just a mathematically elegant way to represent numbers that have both a real part and an imaginary part. They capture the full set of solutions very neatly. Okay. And the key thing is, this recursive calculation of coefficients ensures we are working with exact symbolic values from the very beginning to the very end. No approximations creep in.
It's a fundamentally different way of doing it from the ground up.
Absolutely. It avoids approximation altogether.
So we connect this back to the bigger picture. This isn't just some, neat math trick.
Oh, definitely not. It highlights, I think, a fundamental shift in how we approach what's even considered solvable in mathematics.
Because Ezouidi's theorem doesn't rely on those numerical approximations at all.
Correct. The roots we get are exact, precise. They're not subject to those tricky, error-prone calculations you get with numerical methods.
And that precision matters.
It's transformative. I mean, think about complex simulations in fields like climate science, or maybe the intricate calculations needed for designing new drugs, or even the algorithms deep inside AI. Exactly. In those fields, tiny errors can compound, they can snowball, leading to results that are less reliable, maybe even wrong. This theorem potentially offers a path to absolute certainty in those calculations.
So it could unlock new frontiers in computational accuracy.
Potentially, yes, across countless disciplines where high precision is critical.
So, okay, wrapping this up, what's the immediate practical takeaway for you listening? We've taken this journey into the heart of these really complex high-degree polynomials and revealed a method, Ezouidi's theorem, that really transcends the old limits. It gives exact symbolic solutions where before we only had approximations or we just threw up our hands and said unsolvable.
Right.
It's kind of a shortcut in a way to being well informed about a pretty complex mathematical breakthrough, but one with potentially huge real world implications.
And, this leads us to a fascinating final thought. If our understanding of what unsolvable means can be so dramatically redefined in mathematics, where else in our world might similar breakthroughs be waiting? Where else could we shatter long-held assumptions and unlock exact solutions to problems that just seem completely intractable right now?
You mean beyond math?
Absolutely. Think about biology, physics, maybe even economics or social sciences. What other challenges that we currently label unsolvable might just be waiting for someone to find a completely new lens, a different approach, like Ezouidi did for polynomials?
That's a really powerful thought to end on. What else are we missing just because we're stuck in old ways of thinking?
Precisely. Makes you wonder.